Hello, everybody. Welcome to the blank void that is my office. Since class is canceled today, and there's probably going to be some power outages and all kinds of all of that, what I'm going to do today is make a video of the quiz prep problems from the recitation meeting you would have had today. There's a few perks and drawbacks to this. First of which, I am not going to be able to honor the particular requests from discussion board posts. I recommend you come to an office hour or anything to that effect next week, if that's possible. If not, let's stick to the immediacy of things and make sure that we get exactly what it is we need from quiz prep. So that's definitely a drawback. I kind of hate that. The perk is we're going to go through all of the quiz prep problems, which would never happen in an actual recitation section. But I just kind of want to extend that to you all. So let's do it. I'm going to apologize for the penmanship on the screen because this is a new touch screen, and since I make community college money, I've got two monitors going. Sometimes that can be a little tricky and confusing. So let's start with problem number 1, and let me zoom in so you can see it. And another perk to having not meeting today is you don't have to see my face in any capacity of it. So let me go ahead and dip mine out of there. There you go. So for this problem, what we're given is what is the recursive form of the linear growth. And what this basically means is in order to get to the next thing, I take the one before it and add 45. So to get to P1, I take the one before it, which in this case would be P0, and I add 45. Well, we know that P0 is 20. I've got 20 plus 45. That's going to be 65. Okay. So that's a 65. Now for P2, by that same logic, I'm going to take P1 and add 45 to that. Well, I found that P1 was 65, so now I'm going to take 65 and add 45 to it, and I'm going to get 110. Now, for the explicit formula, recall that the explicit formula is this guy, d times n plus p0. Well, the good news is we already know what p0 is because it gave it to us. That's 20. All right, that's pretty neat. And then the d value, that's our constant difference. That's the thing that we're adding each step. That's also given to us. That was 45. So that's going to be 45 times n equals 20, and that's going to be p of n. And that's my explicit formula. 45n plus 20. Now, the thing that's really nice about an explicit formula is finding p of 100. That's just where n is equal to 100 is really simple. If I wanted to find p of 100 using the recursive formula, I'd have to find the 99th and then the 98th and the 97th. Who has the time? Times 100 plus 20. Well, 45 times 100 is 4,500 plus 20. 45, 20. And ultimately what this problem is doing is getting you familiar with recursion and using that recursion formula to build an explicit formula. They're both wildly useful. So now we're going to go to question 2. For this problem, I've had folks say, well, I didn't need to use anything involving the formulas here. I just used some basic arithmetic. I have no problem with that. Use the basic arithmetic and I bristle at this term, but common sense mechanism to check your work. But it is important to learn how to build a model. So we've got 129 lights first. Okay, so we start with 129 lights. So I'm going to say that's P0. And then each and every week, we're going to add 3 new lights. So my common difference is 3. And I know that this is linear because I'm adding 3 additional lights. It's a constant number of lights that I'm adding each week. If I said I was going to increase the number of lights by 3%, that's a whole different thing. Because as we know, percentages change as the quantity of the thing we're taking the percentage of changes. So you can't say that a percent is a constant increase or decrease. So I've got Pn is equal to common difference times n plus 129. As a note for the quiz, you're not going to get a formula sheet. Okay, so you do need to know these familiars, at least be internalized with them. Okay. And then in this particular case, I know that the n value is 52. So that's how many lights I have after 1 year. Okay, and so now we're just going to go ahead and multiply these numbers. Now, fun fact about me, I have a passion and penchant for making errors with my arithmetic. So I went ahead and just typed that in. And I got 285. Because again, I make community college money, so I have 2 monitors. If you dream big, you can win big. All right, now, I kid. This is absolutely my dream job. I am in hog heaven teaching here. So now we're going to take question 3. This one tripped folks up, and for completely justifiable reason. Personally, I think this problem is, I think it's a good problem, but there is one little flick of the wrist that's not obvious. So what we're doing in the first portion is writing a recursion formula. All right, so I know I'm selling cars, starting with 5, and what I'm doing is to go from 5 to P1. P0 is 5, and then P1 is 7. What I need to do is find the common difference, which is what we would have here. What did I add to the one previous to get to it? Well, to get from 5 to 7, I added 2. So my common difference here is 2. Now, since I already know the common difference, when I'm asked for the explicit formula in the next part, I'm pretty much there. Okay, so now I've got 2n, and now plus P0. So I need to know the initial value, which isn't terribly tricky, but if you use the n plus first week, we'll get there. So if P1 is, well, P0 is already given to me, that's 5. Boom. There we go. So we've got 2n plus 5. Now, here's the trick. I'm in the 4th week. This formula is based on the n plus 1st week. So what I actually have here is 4 is actually equal to n plus 1, not equal to 4. Okay, and most folks will read this and they'll say, oh, n equals 4. That's not the case. N is going to be equal to 3. So what I'm saying is P3, 2 times 3 plus 5, we're going to have 11. Okay. This is going to be where the most mistakes get made. This one's tricky, and it's kind of not my favorite problem per se. Okay. So we'll clear that out. All right, now we're going to actually skip to Take a look at the notes for problem 4. We're going to go ahead and jump to 6. All right. One thing I appreciate about this problem is it requires you to read the problem and really understand what it is that you're doing. So what we're going to do here is, well, let's just go ahead and take a second and read the problem. All right, the thing that's really important is to understand this: T years after 1995. This equation is going to tell us the total average credit card debt, and that's growing linearly, which is generous. And what we're going to do is we're going to find out what the average credit card debt was or will be in the year 2011. Now, here's what students are going to do that's going to make a mistake, or that's going to be their mistake. They're going to say, oh, T is equal to 2011. And if you need to, pause the video for a second and think about why that's a mistake. So that's a mistake because we're saying T years after 1995. So what I need is the difference between 2011 and 1995. And I get 16. Here, the T value is actually going to be 16. Okay, so now what I'm going to go ahead and do is just compute what 412 times 16 plus 5650 is. And I get $12,242. Okay. So that's going to be question 6. All right. The real trick here is identifying what the T value represents. All right. Let's take a look at problem number 7. Now, I understand that this one's multiple choice, but let's just wrap our heads around what exactly it is that we're doing here. Let me make sure here. Am I looking at the right thing? Yeah, okay, great. For this guy, let's think about what's happened. So the rental car company charges $45 first. So if I think about the cost, right, it's going to be linear because I'm growing by 40 cents every mile. So I'm starting at a cost of $45. This is our P0. In this case, we'd probably actually do well to think of this as C0. And my D in this particular context. Well, my D is going to be the thing I'm adding at the time, which is 40 cents. So if I write 40 cents, that's going to be 0.4, right? That's $0.4. We write that as a decimal times N plus 45. Okay, and we'll actually use M because that's what we were told to use. And that's going to be the model we want to use. Okay, so make sure that you are kind of using the proper form here, but this is basically a linear equation, right? So y equals mx plus b. I'm telling you the slope is 40 cents, 0.4. B, I'm telling you the starting cost is 45. Okay, so make sure that you're paying mind to this. And now what I'm asking you to do in this portion, I'm telling you, okay, you're going to drive 250 miles. So now we know m is equal to 250. So what I'm really asked to find here is C of 250. So that's 0.4 times 250 plus 45. I'm going to go ahead and type this in on my other monitor because I'm fancy. I'm so fancy to have a second monitor, but apparently I can't paint a wall in my office. I don't know. Let me get 145. So we get $145. Okay. Now this one here, I've had a lot of students get this one correct through process of elimination, and great, that's awesome. The rub here is I really want you to know the math, what it is that we're doing. And if you don't know that, that may be a problem on the test because, as I've said before, while questions may be on a problem bank, they may not necessarily represent on the test the way that they show up in the problem bank. So you have to understand the math behind it. Now, even aside from that, let's suppose this doesn't show up on the test. This is a very common type of problem. And this is a very important type of thing to be able to do. Okay, so take a second, read the problem. If you need to pause the video to do that, go ahead and do that. Drink this in. Okay, so here's what we have. What I want to do is come up with the model. And we're going to be coming up with the explicit formula, okay? And so we're going to say, all right, C of X is going to be equal to dx plus C0. And let's talk about what each of these things mean. Let's talk about C0. This would be the cost of ticket with 0 passengers. I understand that sounds ridiculous, but that would be our base price, our baseline price before people start buying the tickets and they become cheaper as a result of filling the plane. Now, the D, in this particular context, our constant difference, is going to represent the change in price per ticket. Now, just by reading this, looks like we don't have anything given to us. And that's about true. We don't know anything about the change in the price per ticket. We also don't know what the cost of the ticket would be if no one had bought it. So we can't really build this formula. Now, if you want, you can view this as 2 coordinate pairs, and we're going to need to find our D value from this. There's a couple different ways you can think about it, and there is absolutely nothing wrong with thinking of these all kinds of different ways. So if you want to, you can construct 2 coordinate pairs for finding the D value here, okay? We've got $400 per person. It's going to be my C value. That's my Y value. That's my dependent variable. And I sold 200 tickets to get to that cost. And then we've got 450 here. And that was after I sold 150 tickets. You can say X1, Y1, X2, Y2. If you hear the chickens in the background, I'll tell you the same thing I tell my neighbors. Sorry. You can use your slope formula here. Yes, you do need to have that memorized. And you will get to the rate of change. Let me show you another way to do it. One that doesn't require nearly as much formulaing, because formulas, I don't know, they are very tempting, but they don't, I don't know, they don't simplify a problem sometimes. So let me show you a way to do this without using a formula or anything to that effect. Here's what I see. When I sold 200 tickets, it cost $400. When I sold 150 tickets, it cost $450. So the way I see it is, all right, so there's a 50 ticket difference sold at a negative 50 delta. So what that basically means is every 50 tickets I sell, I've lost $50 in the price. So let's see what that means on a per ticket basis. So every ticket I sell, I lose $1 in cost. Guess what? You would have gotten the exact same thing if you plugged that formula in. If you look at what you did here, you did exactly that. This is just kind of not as intuitive a way to think about it. So I already know my D value is -1, which is great. And there's a couple different ways you could do this next part. And I don't take offense to any way that you choose to do it. If you choose to do it formulaically, there's obviously nothing wrong with that. If you choose to do it non-formulaically with what might be a little bit more of an intuition, that's completely fine as well. The way that I'm going to do this with the formula first, and then I'll explain it in what I think is intuitive language. So if you want, what you can say is, all right, we need to find what C of 0 is. So what I do know is C of 200, I can choose either of these coordinate pairs that I want, costs $400. So what I know is 400 is equal to -1 times 200. If I plug in the n and the x value here, plus C0, and I'm just going to solve for C0. So I get 400 equals -200 plus C0. I'm going to add 200 to both sides. And I get that C0 is equal to 600. Great, dandy, done. Can we do this a little bit more intuitive? Yeah, certainly. Do we have to use this big old formula? Nope. Or do we have to use this formulaic process? Absolutely not. You do not. It is not a huge deal. So what you can say is if I lose $1 in cost for every ticket I sell, I know that with 200 tickets, it's going to cost $400. So I want to go backwards, effectively 200 steps, which means instead of subtracting, I'm going to be adding 1. Really what I'm asking is what's 200 plus 400? Well, that's going to be 600, which if you look at that process, it's the same thing we did in the first formulaic part. Ultimately, these formulas are not made up. They are built from an intuition, but sometimes they're just easier to work with, and there's nothing wrong with that. All right, let's take a look at problem number 10. So we've got a statistician. They're typically a lot of fun to hang out with. And we need to, this f of x really just is a fancy way of saying y. Okay. If you take my pre-calc class, we'll spend a lot of time talking about that. If you don't, it's probably for the best. So we've got x is equal to 7. All that means is I plug 7 in for x. All right, and so what I'm really asking you to do in this first part is just kind of do this computation. And we get 2267. Okay. And this is our estimate for here. For when x equals 9, the only thing we would do is change this 7 to a 9 and type that in. So make sure that you do that. And let's do 12, and then we will call it quits from there. I really like this problem. And what I'm not doing here is I'm not being coy and telling you, like, I really like this problem. It may even show up on your quiz or your tests or whatever. I'm not going to do that because I already give you all the information you need. I'm not here to be cute and all that jazz. So let's just take a look at this first part. Here is the actual real world data that I've got. Wait a minute, come on back. There we go. Okay, so this is the actual real world data I've got. Now, the purpose of a model is to make approximations. Okay, that's what it's supposed to do. I come up with a line of best fit. And this is the equation for that line. Oh, God. Sorry, I used my mouse for that. So this line is our actual model. All right. Now, the first question is asking, is this actually a good model? Well, let's talk about what models are supposed to do and what they aren't supposed to do. What models are supposed to do is help us mathematically predict real-world phenomena with mathematical operations. Now, what we're not saying is compute real-world information. That would be asking a lot. Models are not supposed to be perfect, but they're supposed to be an accurate estimate. So if we look at the relationship between the line and the points, yeah, this model is fine. It's not perfect, but it never told us that it had to be. Yeah, sure, this point is not on the line. Doesn't matter. This point's not on the line. It's close. It's fine. Now, a fair question would be, well, all right, fine. When is a model not a good fit for the data? Well, here's a perfect example. Let's suppose we had a relationship like this. Okay, it starts blowing up. This is what we would call exponential. This model here is not going to be good because as the real world data continues to be compiled, it looks like it's making this kind of pattern. Our model is going to get more and more inaccurate. So we're sort of looking at this as a global type thing. All right. So this model is absolutely fine. I got no beef with it. I think it's fantastic. I think it's great. I give this model a 5 out of 7. Now, what I need to do here is estimate these retail sales in billions of dollars. So what I'm going to go ahead and do is pen this actual model up here so that I can turn that to the top of the screen. This is some zoom technique that's a little bit above my station. There we go. All right, so now it's weird because it writes on the screen that the screen is fixed. It's super strange. So what we're going to do is we're going to estimate the retail sales in 2012. 2012. How does our model actually work again? Well, the X value in our model represents years since 1995. That sounds familiar. We're computing X as a function of years since a thing, not when the year is a thing. That's helpful. So when we get down to it, what I've really done in part B is ask you, hey, what's the X value? And then let's plug it in and find what the Y value is. The trick is we need to find out, first off, in 2012, what is the actual X value I'm going to be using? So I need to find, whoa, not 1950, 1995. We didn't have cell phones then. Weird. Even when I was a kid, we had car phones, and like I had to call my mom's car phone sometimes. That was strange. So then we get 17. Ha ha ha. The mistake that many students are going to make is they're going to plug 2012 in. And what 2012 represents as an X value is the number of years since 1995. And if we're 2012 years past 1995, we are in the year, wait, stop it. Don't pause my share. we are in the year 4007. I don't think we need to worry too much about cell phone customers in the year 4007. I think we have, I don't know if we'll even be around it. I don't even know if there's going to be people. Who can tell? So let's go ahead and do this computation. We get 9.44 times 17 plus 84.182. And let's do that. So we get 9.44 times 15 plus 84.182. Boom. And we get 244.662. Why are you still being so problematic? All right, so if I'm going to round this to the nearest billion, I'm going to go ahead and say 245. Okay. Now, let's not do that. Let's do that. Now I'm asking, when will the retail sales be 233 billion? Okay, well, this is a type 2 problem. I know the Y value is 233 billion. And I need to solve for X. So pause the video and try this on your own first. I'm going to subtract the 84.182 first from both sides. And I know that things have probably gone a little weird here. I don't know why. It's not sharing all the way through the application. I don't know what's going on. But that's all right. I don't know what you're looking at. If it's my desktop, you see my son. Little Swedish meatball looking. And so now we get 148.818 to 9.44x. So now we divide that by 9.44. And we get X is equal to about 15.76, blah, blah, blah. Now look, we're saying year in which. So I have to round this down. So in this case, X is actually going to be 15, because if I round it up, then what's happening is I'm in the 16th year. I've already passed 233 billion. So I've got to round down here. And this is 15 years from 1995. So this answer is actually going to be 2010. In the year 2010, this happens because, remember, X represents the number of years since 1995. And so my answer is 2010. I hope this is really helpful to y'all. Let me know if there's any other way that I can be of service. Stay safe. See you guys next week.